So this diagram would be the heart of the discussion that we'll be doing now. So it's very critical that we understand uh, this diagram well. So there are 2-3 points that we need to understand well. The first point is this point P1. This is the top of the wheel. There's a point P0, which is the bottom of the wheel. There's a point C, which is the center of the wheel, and there's a random point P2, which is anywhere in the on this wheel. Uh, Call it a wheel, call it a disc, whatever you call it. So alternatively, I'll be calling it disc or wheel. So it's a one and the same thing. There's another thing that we need to understand, that the understanding is that this is moving in a clockwise direction with the angular speed of omega. Now you should be very clear uh, about the right hand rule. If this is moving in a clockwise direction with the angular velocity omega, when I apply the right hand rule, basically the thumb uh, would be pointing inside the screen of the laptop. So what I'm trying to tell you is, usually in questions like these, when we'll be solving questions, usually what I do is I consider this axis to be my I axis, this axis to be my K axis, and this vector J, which is going inside the laptop screen, that is the J vector. Now, why I prefer this Cartesian coordinate is that you can easily apply the right hand rule. So from I to J, K is upside. And in our case, what you need to understand very clearly is that the angular speed of this wheel, of this disc, the magnitude is omega, but the direction of that angular speed is given by the right hand rule, and it points in the inside the screen. So basically, if you have to write the uh, omega vector, the omega vector can be written something like omega j. So if you understand this point, you'll be able to do numericals very easily. So be very clear about the Cartesian coordinate that you are choosing. J is pointing inwards, I is in this right direction, K is pointing in the upward direction. So be very clear about it. It will help you a lot. So, for us, the critical equation that we need to understand is the that velocity at any random point is given by, it's basically the sum of two move two velocities. One would be the uh, what is called the velocity of the center of mass. This is our translational translational velocity. Translational velocity. This VR part is comes from the rotational motion. So basically, you'll have studied in your books also that this rolling motion can be said as a addition of two movements, translational plus rotational. So this is what it means. So one would be a translational motion, the other would be the rotational motion. And when you have to analyze the full movement of a rolling wheel which is going towards this side, it is the sum of the translational motion plus the rotational motion. So this is what it means. If you look at this point P2, let me expand this point P2 so that we are able to focus on this well. Now you will be able to look at this point P2. See, point P2 is given by the vector sum of the Vcm, which is the velocity of the center of mass, plus the Vr, which is due to the rotational motion. This VCM, this VCM, this VCM part, for any point on the disk or the or the wheel, whatever you call it, this VCM part would always be same. So what I'm trying to tell is that at P naught, the VCM would be the same. At C, the velocity would be VCM, velocity of center of mass. At P1 also it would be VCM. At this point also it will be VCM. At this point also it is VCM. So the translational VCM, basically what I'm trying to imply is that VCM, the velocity of the center of mass in our rolling motion, is the translational part. Is the translational part. It is always the same at any point of the rolling wheel. Be very clear about that. And what is the magnitude of this VCM? The magnitude is given by omega r, where r is the radius of the wheel. R is the radius of the wheel. You need to be very clear about it. Never get confused about it. At any point, I'll be repeating this again and again because this is a very confusing point. You take any point on the wheel, the velocity is basically the sum of the translational part and the rotational part. What I'm trying to tell you is that this VCM part would always be the same. This part, the rotational part, will change. We'll discuss that. But be very clear that the VCM part would always be same. And this VCM part, uh, the magnitude of this is given by omega r. And if you want to have uh, if you want to have the vector formula for VCM, the vector formula for VCM would be given by omega cross r. Omega cross r. So this vector would always be the same. If I have to calculate, if I, just to illustrate, let me, because this VCM will always be the same, this VCM part is always the same. So I can take any, to calculate the VCM, I can take any point. So for ease of calculation, I'll be calculating the VCM at P1. I'll be calculating the VCM at P1, and you will realize in few minutes why does this help. So this is my coordinate axis. See, if you understand, what I'm trying to tell you is that if you understand this funda and you try to do any JEE problems, I also have done JEE problems. You'll see the link below. So for example, if you understand this funda, so any JEE problem, so a problem like this, you can do this easily. A problem like this, you can do it very easily once you understand the core concept. Because see, in JEE, fortunately, unfortunately, unless and until you are clear about the concept, it becomes difficult to solve the problem. So this is my, as I've discussed, this is my I direction. This is my J direction, and this is my K direction. So as I have discussed, the omega, the angular velocity can be given by omega j. Now I am calculating the vector form of the translational component of the velocity VCM at P1. And once I've calculated at P1, it would be the same as P2 at C, at P0, at any point P3, because I have promised you this, that this VCM part would always be the same. So the magnitude and the vector component would always be the same. So now I just have to do the cross product of omega cross r to calculate the VCM. Omega, I have omega j cross. Now at P1, because the radius is r, and this is how the radius looks like. This is how the radius looks like, and it is pointing in the k direction. So I can write this as r k. Hope this is making sense. Now I understand. So this is j uh, for in when I'm doing the cross product of vectors. So this is I, this is j, this is k clockwise direction. So j cross k would be equal to I, and this is omega r I. And of course, this is what it is. So VCM in vector notation can be written as omega r I cap. So the magnitude is omega r, and the direction is in the I direction. See, I am repeating again and again. This will help you a lot when you are doing the JEE questions. So, for example, uh, I have done this question using the same things that I am discussing here. So, it will be very easy to do questions like these. So let's come back. So now till now what we have discussed is that this VCM in terms of vector notation can be written as omega r I cap uh, in the I direction. So uh, let us assume I am trying to calculate it at p1 only, at p1, velocity at p1, at p1. Now this component is Vr. Now Vr is given by this is the rotational part of the velocity. So the rotational part. So for rotational part, again the formula which will be used would be omega cross r, and we have calculated here this is equal to omega r I cap plus omega r I cap. So for P1 it will be equal to 2 omega r I. I hope this is making sense. I'll delete all this. So what this implies is that at P1 it is the translational part is omega r I plus omega r I. So this is equal to 2 omega r I cap. So I hope this is making sense. Now let's look at P naught. Now this will become very easy. This will become very interesting. So P1 is done. At P naught, at P naught, uh, VCM part, the translational part is omega r in the I direction. Plus, now I have to calculate the rotational part. The rotational part, the rotational part, rotational part would be given by omega cross r. But now what will happen is that omega is given by uh, omega I cap cross the r is in the downward direction. So this is equal to uh, minus r k cap. It's in downward direction, no? Because this is like this. Because my axis is like this. I, j, k. So because the r vector for p naught, the r vector for p naught is in the downward direction, is pointing in the downward direction. So that is why it is minus rk, minus rk. So uh, sorry, this is j. I'm sorry. This is, yeah, this is j. So j cross I again is equal to minus omega r I. So if you are with me till here, what you will realize is that the Vcm is the same. It is equal to omega Ri. But now the rotational part is in this direction. So this is minus omega Ri. And that is why this P naught, that is why you'll find in the books when they write that P naught is equal to 0, that the lowest part of the rolling wheel is equal to 0. Hope you are here. Uh, Hope it is making sense till here. Let me recap what we have discussed till now. Let me recap what we have discussed this now. See, what we have discussed till now is that VCM at any point on this would remain the same. It will not change. It will not change. In our case, we calculated this VCM. In our case, we calculated this VCM would be given by omega r I cap. Omega r I cap. This is the Cartesian plot that we made. I, K, J. So VCM in our case is omega Ri in this direction because the wheel is rolling in this direction. Okay. At P1, what we calculated was that the velocity is given by two components, the translational part plus the rotational part. At P1, because VCM is always equal to omega Ri, this is omega Ri. The rotational part incidentally also comes to be omega Ri. Omega Ri. So that is why at P1 you'll have 2 omega Ri. That is the addition of these two. But at P naught, what happens is the translational part is in this direction, but the rotational part is in this direction. See, technically also this makes sense because the wheel is moving like this, moving like this. So they are in opposite direction. So that is why at P naught you'll have a velocity which is 0. Now if you see again, if you haven't understood till here, now this will again start making sense. Look at point C. Look at point C. The VCM is in this direction. So the translational part is omega r in I cap. But the rotational component is 0. Why it is 0? Because the rotational component is given by omega cross r, and at point C this r is 0 because it is at the center. So that is why the velocity is omega ri. So that is why this is what is written in books, and now I hope it makes sense that at these 3 points, this is 2 omega ri, this is omega ri, and this is 0. I hope this is making sense till here. And now coming to any random point. So for example, a point like P2. Now P2 again, VCM is in the same direction. So VCM will always be omega Ri, where R is the radius of the wheel. Always remember that R is the radius of the wheel. But when you have to calculate this component, this VR component, this would be given by omega cross R2. Why R2? Because this R2, this position vector, you have to find the cross product of omega into R2. From that, you will get omega R2. So, at P2, velocity at P2 would be given by omega Ri. This part, translational part, always the same, plus omega cross R2 again in the I direction. But then you will have to calculate the value of omega cross R2 because it will depend upon where the position vector R2 is. The first part, the translational part, is always same. It is omega Ri, it would always remain same. But the second part, the omega would be the same. You'll have to calculate the R2. Basically, you will have to define the R2. In one of the questions I have done, I discussed this in detail. So, for example, in this question, I'll put the link also. I had defined the point. This is how I defined the points, P and Q. So I actually calculated the vector of OQ, the position vector of OQ. I calculated the position vector of OP, and then I took then I this is how again the Cartesian coordinate were defined. Then I took this is how I calculated the omega cross uh, the position vector. Again, I calculated the omega cross the position vector. So you can have a look at this video also. It will help you a lot. It's a pretty detailed video, very nicely made. So when you look at this formula, when you look at this formula, so this is basically a general way of calculating the velocity at any point of the wheel. So this can be uh, this can be written as a VCM plus omega cross r, where r is the position vector of any point on the wheel. There's a random point, any point of the wheel. You can write this as uh, omega r I plus omega cross r, where the capital, see, you have to understand the difference between these two r's. The capital R is the radius of the wheel. So omega ri, because it remains constant, it will always be the same. But the small r is the position vector of the wheel. What do I mean by the position vector of the wheel, of the point? So for example, in this case, this would be the position vector. At this point, this would be the position vector. At this point, this would be the position vector. So position vector can be defined. Uh, so for finding the cross product, you'll have to have the coordinates of the position vector to define. So I hope this made sense, and let me take you through the notes quickly. More or less, we have finished the discussion, but I'll just take you through the I'll just take you through the notes again. So rolling is simply translation of the center of the mass plus the rotation about the center of mass. We have discussed this. Basically, uh, rolling can be defined as sum of the translational plus the rotational. You can define this as a sum. So this figure is important to understand. Uh, Step one, uh, the velocity at any point can be written as this is the translational part. This is the rotational part, sum of the translational plus rotational part. So for rotation part, omega r, then this is a condition for rolling without slipping. We calculated Vp naught is equal to 0. What that implied was that the lowest point, we discussed, this is at 0, and uh, the top also we calculated, V top is equal to twice of Vcm. So in short, this is what we discussed. Uh, Vcm, velocity of center of mass, and at any point the translational component would always be r omega, where r is the radius of the wheel. If you want to calculate the velocity at any point, it will be given by Vcm plus Vr, where r is the position vector of the point. At the uh, bottommost point, this is P naught. Uh, at the This is 0. The velocity would be 0. At the topmost point, it will be twice of Vcm. At the middle, it will be Vcm. And this can be holds for all rolling bodies, disk, sphere, cylinder, etc. Uh, so, so hope this part made sense to you, and please have a look at the numerical part also, because unless and until we look at the numerical part, things don't make sense. So for example, this is a small numerical that we can do to understand the nitty gritty. A sphere is rolling without slipping on a fixed horizontal surface in the figure A. Is point of contact, B is the center of sphere, and C is the topmost point. So uh, if we compare this with uh, our discussion, so this is P1. Sorry, pull it here. Yeah. So this is my P1. This is my C, and this is my P naught. I just want to compare it with our the discussion that we are having now. We just had. So they are asking you to compare. Now we understand that at as per this diagram that at A the velocity would be 0. So that is why VA is equal to 0. At B it would be the velocity V. I have assumed it to be V. And at VC it is twice of V. I've just calculated it to, I've just assumed it to be V. Let me rub this so that we don't get confused. So now VC minus A, VC minus VA, VC minus VA. So VC minus VA would be twice of V. And VB minus VC, VB minus VC, VB minus VC, V minus 2V is minus V. So this is minus 2V. So this is incorrect. VC minus VB is equal to VB minus VA. So VC minus VB is 2V minus V. So this is V. And VB minus VA is V minus 0. So this is correct. Uh, VC minus VA, VC minus VA is 2V minus 0. So this is 2V. And twice of VB minus VC, VB minus VC. So V, this is, see, they have put a modulus sign. So that is why twice of modulus minus V would be equal to 2V. So this is also correct. And if we look at the D, so this is VC minus VA is 2V and 4 times VB. VB is 4. So this is incorrect. So our correct answer is B and C. So this is a small example like I have used to illustrate. You can have because this numerical will take time, so I'll solve this in another lecture. And I have done this. I have discussed this also in a separate lecture. You can have a look at that also. So I hope this was useful, and uh, you learned a lot of new stuff. So thanks a lot for watching, and best of luck.